Let's take a look at how to identify if one of these tables represents a linear relationship. First, with table 1, we want to take a look at the change in y, which is 5, and the change in x, which is 1. Here, the ratio would be 5 over 1. The change in y over the change in x is 5 over 1, which is 5. We then take a look at the next change in y, which is 2, and the next change in x, which is 1, and 2 over 1 is 2. Because these are not the same, this is not a linear relationship. For table 2, we take a look at the same idea. The change in y is 10, and the change in our x value is 1. 10 over 1 is 10. Let's take a look at the next change in y and change in x. Here the change in y is 10, the change in x is 1. So again we have 10 over 1, which is 10. Because these are the same each time, this is a linear relationship. Let's take a look at table 3. The change in y is negative 2 because we're going down by 2, and the change in x is 1. So we have negative 2 over 1 for our change, which is equal to negative 2. The next change in y is negative 2 over 1. But then we have a little problem here. We have a negative 4 change and a positive 1 change, which gives us negative 4. That's not the same as negative 2. So this is not linear. For part B, we want to write an equation that represents a linear relationship. So table 2 is the only table we have that represents a linear relationship. All of our linear relationship equations are going to be of the form y equals the rate times x plus the y-intercept. In this case, our rate is 10 over 1, which is 10. So we have y equals 10 x. Our y-intercept is simply the value where x is 0. And here x is 0 and y is 0. So our y-intercept would be plus 0. You don't have to write this, but if it makes you feel more comfortable about adding your y-intercept in there, feel free to do so. C asked us which table represents a proportional relationship. For a relationship to be proportional, it has to do two things. One, it must be linear, which means it has to be a line. Two, it must go through 0, 0, or the origin. Table 2 is a line, it's linear, and it goes through the point 0, 0. So table 2 is a proportional relationship. We identify the rate of change in a graph the same way we identify the rate of change in a table. We need to look at the change in y over the change in x. In this first graph, we want to go from one point to the next. Y changes by 10, while the x value changes by 2. You have to pay close attention to the scale on your axes. So in this case, the change in y divided by the change in x, 10 over 2, gives us a rate of 5. For the next graph, we're going to take a look at this change. The y changes by 20, and the x change is 1. So the rate for this graph is 20 divided by 1, which gives us 20. For this last graph, again, we pick 2 points. The difference between this point and this point The change in y is 10, and the change in x is 1. So our rate is 10 divided by 1, which gives us 10. If we're looking at the unit, it would be 10 miles per hour, because it's our change in y, which is miles, over our change in x, which is hours. Problem number 3 asks about Jason participating in a walkathon. The equation here represents how much Jason will earn for each kilometer that he walks. The rate is 2, which represents $2 for each kilometer that Jason walks. The 50 represents a flat fee. It's also called our y-intercept. This is the amount of money that Jason will start with no matter how many kilometers he walks in the walkathon. This equation represents the amount of money Sierra has in her lunch account each week. If we take a look, we can see that the rate of change is a negative $6 per week. That means that Sierra is using $6 each week. The 40, which is our y-intercept, represents how much money she starts with in her lunch account. The following problem is a great example of how we put together everything we have learned about tables, graphs, and equations. Mark opens a bank account with $20. Each week he plans to put in $5. Make a table to show the total amount of money Mark has in his bank account. Show the amount he has in his account from 0 to 10 weeks. For our table, we're going to put weeks on the left side, and on the right hand side, we're going to put his total. For week 0, Mark has $20 in his account. That's the amount he started with. After 1 week, he has $25. After 2 weeks, he has $30. After 10 weeks, Mark will have $70 in his bank account. To make a graph for this table, we need to consider how large our graph is and how we want to split up our boxes. In this case, we need to go from 0 to 10 weeks. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lines. So we can go by 1 on our x-axis. This axis is labeled weeks. On our y-axis, we have our total. And for our total, we need to be able to go up to 70. So I'm going to go by tens. 10, 20, Be sure to note that I did not start at 20. Whenever you are labeling your scale on a graph, you need to keep the scale consistent, and we always start at 0. To graph these points, we're going to start at 0 weeks. The total was $20. So 0 weeks, $20. 1 week, $25. 2 weeks, $30, and so on. Once I've graphed all my points, I can draw a line through them using a ruler or straight edge because we want a nice straight line. And we always want to put an arrow because that line will continue forever. If he continues to invest $5 per week in his bank account, this will tell us how much money he has. If we want to write an equation to represent the total amount of money he has after W weeks, we have T for our total equals, the rate in this case is the $5 per week that Mark is putting in. So $5 per week plus his starting amount of $20. In which week will Mark have a total of $60? Total of $60. That tells us that we need to substitute 60 in for the total in our equation. So 60 equals 5W plus 20. To solve this, we subtract 20 from both sides. 40 now equals the 5W. And to undo the multiplication that's happening with our variable here, we do the opposite operation, which is to divide by 5. And we get that at 8 weeks, Mark will have a total of $60. We can check this by looking at our table. 8 weeks, $60. We can also find that in our graph. We go to 8 weeks on our x-axis, move up to our line. Here we see this is where 8 weeks intersects with our line. Then we move across to the y-axis to find that that's at $60. To solve the following two problems, we're going to use substitution. For the first problem, it says find y if x equals -2. Anywhere we see an x, we're going to substitute in a -2. So y equals 2, here's our x, and I like to use parentheses, times -2 plus 10. Y equals 2 times -2 is a -4 plus 10. Y equals -4 plus 10 is a +6. To solve the next problem, we need to substitute 10 in for y. Be very careful that you pay attention to which variable they give you a number for. So anywhere I see a y, I'm going to put the number 10. Y, instead of y, I'm going to put the 10 equals 2x minus 2.5. Now we are solving for x. So we need to get rid of this -2.5. And to do that, we're going to do the opposite, which is +2.5. And to keep our equation in balance, we do that to both sides of the equal sign. 12.5 equals 2 times x. Now we need to do the inverse operation of 2 times x, which is to divide by 2. And we get that 6.25 equals our x. How do we solve when we have variables on both sides of our equation? The first step is to get all the variables on one side and all the numbers on the other. In this case, I'm going to start with the -4x. And in order to cancel out the -4x from this side and move it to this side, I'm going to add 4x to both sides of my equation. Now we have 6x plus 15 equals 27, and the -4x and the +4x cancel each other out. The next step is to now move the numbers that we have on this side over to the other side of our equation. So we have to subtract 15 in order to cancel out a +15. And whatever we do to one side of the equation, we must do to the other. Here we're left with 6x, these cancel each other out, equals 12. Last but not least, we have to divide out our 6. We get x equals 2.